Thanks, Steph. Hey, I'll just kind of take a couple minutes here. See, we got people joining slowly here. Um, Couple points again. Thanks to I want to thank Chuck and Stephanie for helping organizing this webinar. Um, we had 9 different countries that signed up for this webinar, which I think is pretty impressive for a company of our size. And I'm pretty excited about that today. Real quick, I want to talk about our technology real quick and our company. We've been in existence since 2011, and again, I'm just going to kill a little time here while we have people joining. Primary focus of our technology is we focus on high pulse power to help solve some of the challenges that our customers are having in their wellbore. There's a few advantages. It's a green technology. We're not introducing any hazardous chemicals, low energy requirements, and Chuck's going to go into this more in his presentation. Minimal people offshore, low PUB, which is always a challenge for customers today, and a small footprint. We've helicoptered our tools offshore. I'll talk about our jerseys as well. You can see Chuck, Steph, and I, we have our little Blue Spark jerseys on. We're pretty proud of these. We get these from the first day we sign on with the company. It kind of represents that we're all in this a team, and one of our core values is me over we over me, which means take care of yourself. You take care of your teammates as well. I don't think that's ever been more important in the last couple of months when we're all kind of working at home. Some of us are trying to learn long division and teach our kids grade 5 math again, which is easier for some than others. But we're getting it. And but while we're all taking care of ourselves and our family, it's still important. We have a business to run, and we're still growing and expanding, and that's also very important to everyone involved. So the jersey, kind of when we come on as Canadians, we think hockey is the ultimate team sport, and we all take care of each other. Every member of our team is extremely important, and this is what the jersey represents to us. I don't know if we got some results from our first poll. I think we've got.
There we go, Steve. Yep.
All right, so let's see what that is, Chuck. So everyone, dark blue narrowly wins. So we'll continue from this. Stephanie, I'll leave it to you, and we'll get going with Chuck's presentation.
That's awesome. I'd like to thank everybody for taking time out of their busy schedules to join us today as well. And I'd like to introduce Charles Fensky, whose main focus with Blue Spark Energy is client applications. On to you, Chuck.
Thank you. And we go there. Thank you very much. So my name is Charles Fensky. I look after particularly a project manager for Blue Spark, and what I do a lot of is actually customer applications and finding different ways of actually using the technology. What I'm going to share with you today is a presentation that I gave at the SPE Formation Damage Conference in Lafayette earlier this year. What this presentation relates to is unplugging standalone sound control devices with Shockwaves, but really it's an experimental study of that process. I would like to thank the generous contributions and insightful contributions of my co-authors that made this possible. I'd also like to thank our sponsoring organizations, which gave us the opportunity to share this knowledge with you today. Today, I'm going to introduce to you a new method. This method is a cost-effective wireline deployment that requires minimal personnel on well site. Really, it's just one tool that I can run into a well. It's a method that's environmentally safe and doesn't require the use of chemicals. With a chemical, you have to actually get it to location, use it on location, and then deal with the aftermath of this chemical as it goes through your production facilities. This is a method also that has low operational risks to the sand screens and completions. What I'm going to share with you today is the results of cleaning some of those completions with different scales and high pulse power. So let's start off with a problem statement. In a well where you actually have formation fluids coming up, some of them may be water, some of those waters may actually have natural ions occurring. As those ions transition up the well, they go through different pressure and temperature changes And there may be, and there's typically cases where they actually lose their solubility and start accumulating. So we can see them accumulating at the entrance portion in the well over the perforations. We can see them accumulating over the tubular as it comes up, as the pressure and temperature conditions change. And in extreme cases, they may actually block off or prevent the access to the wellbore itself. This phenomena occurs in the tubing and casing. It also occurs actually in the sand control device themselves. This device that was intended to actually filter out those fines and debris to allow going through can also become blocked up with scale and debris as well. This scale can actually start plugging up this flow path or actually binding up the device, the items themselves. So I'm going ahead and launch our next poll.
So this one's just a yes or no question. Do you have scale issues in your well? Give a moment for some answers.
All right, so let's go ahead and end the polling. I'm going to share the results.
Hey, Chuck, that looks typical to what we see from a lot of our customers, that scale, especially in some of these longer, older assets that people are trying to get the last bit of production out of. That scale seems to be a challenge.
Yeah, so when the water starts flowing, those ions start contributing too, and it's unfortunately a fact of life. Yeah.
Yeah.
Okay. All right, so let's go ahead. So what we talked about a little bit earlier was related to what the Blue Spark tool does is it transforms a small amount of energy and it converts that energy into high power shock waves. Why a small amount of energy is reasonable is we still have a finite wireline cable to deliver that energy into the well. So what we have here is an example of a sample that was provided by a customer. And in this sample, the flow paths are blocked up with scale and debris. So I'm going to start a video now, which is going to give you a visual representation of that transformation of electricity into mechanical shock wave, and let's see what happens. So the tool does a series of pulses where it actually converts that energy and releases it. And you can see those pulses actually transforming and breaking up that scale and debris. So let's have a closer look. So on my left was the original sample. We can see the flow paths are now have a blocking mechanism, which is a combination of sand grains, combination of calcium carbonate in this case, and some iron carbonate or a corrosive type scale. Now with these blockages, it's very difficult for the fluid to come through. When we use the application of high power shock waves, what we observe is those blocked areas are now been cleaned up. So now the fluid can actually flow in and out as desired. But what's more important about that at this energy level, we're not actually harming the actual ductile materials, which are the metal. Any of the brittle materials, which are the scales, those are broken up and fractured, but the ductile materials of the sand screen are unharmed. And also we observe the same thing in wire wrap screens and also casing and tubing as well. In this paper, we talked about an experimental process of actually cleaning up these devices with shock waves. We actually used 4 samples that were retrieved from a well with different types of scale that were causing blockages. We used the actual downhole tool like you would use in a real well. And then we pulsed it just like you saw in the video where we actually gave it those shock waves to break up that brittle material. And then we observed in this case, the cleaning effect of actually, as we applied more of those shock waves, how much of those slotted liners are actually cleaned and opened. This is an example case shown at the bottom of the slide here. We start off with 0 pulses, so all of the flow paths are blocked up. You can see them lights through. As we do 15 pulses, we observed it there. We see some cracking actually beginning, but they're still not opened. At 30 pulses, we observe for particularly precipitate scales such as calcium carbonate and barium sulfate. We're observing actually the flow paths opening up. We then continued it to 45 pulses and 60 pulses. What was key at the 60 pulse range, we were observing actually the corrosive or iron oxide based scales were getting cleaned up. And we looked at that for the different types of samples that we're going through. In addition to actually looking at the actual cleaning, we also looked at the scale themselves. As you'd expect in a sand control device, we would actually have the silicon dioxide and fine materials accumulating in, that's their job. But what was also there is we also saw this glue or bridging agent also present and related to the different scale elements as well. So this is the item that was binding up and locking those in place. In the samples, we had different contributions of calcium carbonate, different contributions of the iron oxide, and then different contributions of the actual solids materials in addition. So I'm going to go ahead and launch another poll now.
Hey Chuck, while you're launching that poll, I'll just real quick, people are joining late here. The Q&A, please just ask any questions. We're getting some questions come in here. We'll answer them at the end, but I just want to make sure that people understand that just if you type the questions, we're seeing them. We'll answer them at the end of the presentation.
Thanks, Steve. So this poll is, which scales are most common in your wells? Multiple choice again. Calcium carbonate, barium sulfate, iron carbonates, iron sulfides, or other. This one will give an extra minute here just to let everybody choose as many as they can.
Yeah, so in different places and different stratigraphies, you're going to have different scales, which makes perfect sense.
Yeah, we've seen in the North Sea a lot of the top two, lots of land wells in North America, iron carbonates and iron sulfides that be more challenging, it seems, in water steam injection type areas.
Mm-hmm. Okay, so let's go ahead and close up the polls.
Yeah, it seems to be, we see a lot of calcium carbonate, Chuck.
Yeah.
That seems to be the largest response here as well.
I'd say it's a very common, binding agent of the different sandstones and limestone reservoirs as well. So. All right. So in this study, we talked about actually taking samples of that scale. What we did is, in addition to that, is actually of the pieces that were broken away compared to the ones that were not broken away, we actually observed that when we actually magnify them with a scanning electron microscope and some higher resolution, we can observe in those brittle materials, those shockwaves are actually making micro cracks and fractures. So whether that be in the calcite or calcium carbonate or in the Fe based, that's the key element of this methodology, is the fact that with those brittle materials, when they're applied by shockwaves, they fracture and break up. That what breaks up the glue, which is actually what releases the rest of the structure as well. We also observed that where you have combinations of items, where you actually have calcium carbonate and silicon dioxide or a ceramic type material, those brittle items related to the calcium carbonate are where we're starting to actually see the fractures occurring. The actual formation materials that relate to that are much tougher, and at our energy level, we're not seeing any damages to the sand grains themselves. So there was a question that actually came up related to, can we actually look at actually working in ceramic sand screens? To date, we haven't, but that being said, when you look at this methodology, it would make sense that at our energy level, we're not going to be harming some of those ceramic coatings because they're much tougher than the calcium carbonate or the barium sulfate that we can do at our energy level. So this methodology is quite unique, and it is breaking up that weakest link of the calcium carbonate or brittle scale, which is causing the flow mechanism to open up from there. What is also in the paper, we actually went through several different case studies from around the world. I'm only going to hit on a few of them in their time window that we have allowed for us today. So the first one I want to hit is actually where we actually use the BlueSpark tool to do two different tasks in the same well. Task A related to an accessibility issue of actually in a well where there was scale actually accumulating on the ID of the wellbore. So we can actually see in the caliper log how some of that wellbore has now been shrunk as that scale has been accumulated around it. As we applied those high power shock waves, we actually observed that scale being broken up, and where the shock waves were applied, the scale was broken off the wall and into smaller pieces, returning it back to its original ID. What's also key about this application is we actually did two jobs in the same well. So although we cleaned up the area in the tubing and casing, we actually went deeper into the well and actually pulsed over the perforated interval as well. This also had a disease or a challenge of actually where the scale had accumulated in the perforation throats, restricting flow. So by breaking up that scale, opening up that flow path or opening up that door, we're actually able to get flow to actually start coming back through the well again. The second case study I'll hit on was actually a 9-well aggregate of wells that were done in Texas. But what was specific about this one is the challenge was to remove barium sulfate scale. This is a scale that has a lot of operational challenges to remove traditionally. Over these 9 wells, we actually observed a aggregate 45% increase in oil production and a 72% increase in gas production. These were the desired effects of what they were looking for. What was also observed was actually a 0.5% decrease in water production. How does this happen? The application of shock waves are actually very specific wherever the wireline tool is located. What that allows you to do is selectively treat where you want the fluid to flow, but not actually treat areas where you don't want the fluid to flow. So you can stay away from water producing areas and just target where the primary oil production is coming from, for example. So as a summary of the case studies that were presented in this paper, one of the items observed related to calcium, where our primary challenge was calcium carbonate or actually barium sulfate or any other of these type of scales. We actually observed positive results, whether that be the result of looking for increased oil production, opening up those doors, getting that fluid to flow through, or if the desired result was to remove actually scale and debris from different downhole items, whether that be a plug gas lift valve, whether that be a subsurface safety valve that actually wasn't sealing or had been stuck shut. Applications of those high power shock waves to break up that scale has been effective. This has been done in vertical wells, deviated wells, and actually horizontal wells. This has also been done in actually different places around the world and actually different pressures and temperatures. One of the items which has actually been quite popular has been related to work that's been on light well intervention vessels. So this is a particular environment where POB or number of people on site are actually quite limited or critical. An item where you really need a small footprint, and an item where you can have one tool that can actually do multiple different jobs. So being able to remove scale from the actual ID, being able to repair a downhole device, and actually even open up some flow became very beneficial from a single device. Let's go ahead and open up our next poll, please.
Okay, so which items would you consider using shockwaves to clean scale from? Choose as many as you'd like. So sand screens, frac packs, slotted liners, tubing, casing, subsurface safety valves, gas lift valves, nipple profiles and other ID restrictions, or maybe you have something that's not named here. Give that a few minutes. There's quite a few to choose from.
I think that's the big challenge is that this scale of debris affects many places in a well. It doesn't specialize. So if you have all these different things in your well, you can get affected.
Mm-hmm.
Yeah, and I think we've listed most all the treatment intervals that we have had experience with treating in the past.
Yeah. It's really wherever there's scale, it's an application that can work with that. Yeah.
And Chuck, we're still getting questions in here. We'll encourage more, but we've got a few coming in here, and we'll get to these at the end of the presentation.
I'm gonna go ahead and close up the polling.
So, sand screens win. I guess that makes sense from the topic of your presentation, Chuck. That's great. We also got subsurface safety valves coming in a close second, which we've had a lot of experience with over the last couple of years in Denmark, Norway, helping some customers there with some challenging SSV issues that they have with scale.
Mm-hmm. All right, so I'm just going to conclude our presentation here. So the application of high power shock waves has the ability to break up brittle scales. So we see that causing those microfractures, which are breaking up that structure. The shockwave cleaning does not harm the completion equipment itself. So this relates to that ductile material, the metals being able to absorb that energy, but our brittle material of the scales not. This has been a very effective method for cleaning up scale problems at many different places in a well, whether that be actually at the flow face or as they work their way through. And it really is a solution where the challenge is brittle scales. So I'll go ahead and launch our final poll.
Okay, so do you think cleaning scale with shock waves is a technique that you would consider in the future? Yes, no, or you're not quite sure? Then we can answer that.
So really what I wanted to share today was really the methodology of what's actually going on when we say we're doing this. And it's just breaking up that brittle material, which is the glue, which then lets everything else come apart from there.
Yeah, and Chuck has had a few case studies in his presentation here. You know, one of the questions we had here was about low rate case studies that you're showing. We have multiple other case studies that we could share. Please reach out to us when we'll give you some information here to reach out to us, but we've got ample information we can share of successes in high and low rate wells. Yes, that's a great answer. I like that. For the one person that said they don't know,
we'll help you.
We'd love to talk to you about the challenges or the questions that you still may have.
All right. So I'm going to go ahead and so now we'll go to the question and answer session. If you have any questions that you have for us today, please enter them into the Q&A box. That's the only methodology which you can actually get it to us. Likewise, if you have additional questions, please feel to contact us at webinar@bluesparkenergy.com. Please follow up with Steve Patton, which you've introduced you already, and also myself going from there. And with that, we'd like to open our question and answer session.
All right, Chuck, we've got a few, and I'll just kind of start going through these. I'll grab some of them, and some I will pass off to you. One here, we got came in before you kind of addressed, someone asked about horizontal wells and if we've treated horizontal wells in the past and how we did that. That's an easy one, so I'll take that. So yes, our first actual sand screen treatment offshore was a horizontal well in Norway, and we did use a tractor there. We have also used e-coil to deploy our tool in horizontal wells. We had a couple here. This one's any experience of breaking the silica scales observed during ASP flooding process? These scales are very difficult to dissolve by chemicals.
Yeah, silicate scales are quite nasty, and they really occur in those thermal wells. We have had samples that were provided to us from operators in Canada with silicate scales that we've actually pulsed. With them, they definitely do take a lot more energy and a lot more power. So although not captured in this study, you'll be looking at actually doing a lot more pulses per depth to actually get them to shatter and to say it's some more energy, but they are definitely a more difficult one to handle. And in some cases, they actually become functioning like the sand themselves. So it's a much more difficult challenge. I'd like to follow up with more directly on that one.
Yeah. Can it clean organic scales as well as inorganic?
So the definition of organic particularly relates to actually carbon contribution. So not shown in this example, particularly when you do the XES, is that a lot of these scales are always a mixture of things. So that would be related to actually whatever happens to be in the neighborhood at the time gets built into that structure. So a lot of these scales did actually have some carbon or some hydrocarbon items related into them. That being said, when the structure was scale related and we broke up the brittle materials, we upset that house of cards and caused it to come apart. When it transitions itself to a more extreme case where you have a large amount of waxes or asphaltenes, those are very elastic or pliable materials and are not as effective with high power shock waves. So really it depends on how much is actually, say, your wax and how much is actually scale. As long as a reasonable portion is actually the brittle materials, we can actually break that up.
Okay, excellent. We're getting a bunch here. So what are your experience with your pulsed energy? got another 5 popped in and I just lost one. It's around ICDs, Chuck. What is our experience with pulsed energy propagating through ICDs, non-perforated base pipes?
Okay.
And we're getting a lot of this now in Norway.
Okay.
Seems to be a lot of completion as well as West Africa.
So I'll spool it back a bit, and I'll just give you the thought process of what's going on. So we have our wireline tool. It makes that pulse or that shock wave in the wellbore, and then it travels with line of sight to go until it interfaces with the item itself. So with an ICD, you have a flow port, and then you have some controlling items that are actually inside. So if the ICD related to wherever that wellbore interval related to the flow port, we can actually definitely clean up where it's going to be able to come in. Where you actually get a tortuous path around a corner, you can imagine those shockwaves having to echo and work themselves down. And if those flow paths are very small or very tortuous, it'll be difficult to actually get a good penetration all the way into them. It may occur with a sizable amount of time, but it's a very difficult problem when you have that complicated device, which has actually been scaled or gummed up inside. That being said, where you have the entrance into the wellbore with the ICD, that can actually be quite effective to actually open that up. And you'll get a little bit of propagation inside of it, but it won't be as intense. Does that capture what the question was, Steve?
I think that's it, Chuck. I think we basically need to have a flow path in order to get the pulse through. I mean, I think that's what we're asking here.
I mean, it doesn't turn right angle corners to go around the various places. It really needs that line to coming into it.
Yep. Yeah, and we've been doing some work with some other service providers with drilling holes through base pipe and then pulsing in behind it. We're doing some testing with that now. So there's some applications that we're working on now that people have some of these base pipe completions. I just shared another one, Chuck. Can WASP be used in liquids such as mud or drilling fluid?
The easy answer is yes, and I'll explain why. So we make that high power shock wave, and it needs a medium to actually transmit that energy to wherever it's going to be interfacing with. So as long as that medium is relatively incompressible, so with items like water is great, produced heavy oil, most oils are just fine. Drilling mud will be good as well. Those items are fine. Our biggest challenge is where you have a large amounts of that volume is actually gas. As you can imagine, gas is like a shock absorber. So if you have a high concentration of gas, that'll actually absorb the shock and it won't. But if it actually is a liquid or a traditional liquid, it actually works really well.
What are the greatest risks for the tool not being effective? And I think you just got that one, Chuck. In my opinion, it's the wellbore conditions itself with gas. But
so risk is a big question because a lot of people have different perspective of what risk is. One portion of risk is actually taking the tool and actually getting it to where you want to go in. So that relates to basically we have a design which is very slick and uniform. So as long as there is an ID that we can possibly pass through, and in some cases we can even pulse through some of the restriction, we can get ourselves in and out without getting stuck. Another risk which we talk about in this paper relates to not actually harming. So basically at the 1 kilojoule energy level, we're not actually having enough energy which can actually damage any of the completion of items. So that's also our biggest risk there is basically we go in, we go out and nothing happens, but we're not going to make the completion or harm it from there. And the other risk is actually relates to some of our operational efficiency where we take a lot of steps on the pre-job planning, on the tool checkout, such that we're very certain that when the tool goes past the rotary, it's in as good a condition to be successful as possible. So those are the different aspects of risk. Yeah.
So Chuck, it's almost like you've answered some of these questions from customers in the past, because here's another one that I think you just answered.
Okay.
About the risk, but it's also, I think, an advantage of our tool being a slick body tool. But if we actually run into a scale bridge that the tool cannot pass through, i.e., can we shoot pulses to remove that or keep the tool moving south?
Yeah, so basically, let's suppose you land on the bridge itself. You do those pulse action. It can look a short distance below. Basically, that's where the energy has enough amplitude to actually break up the scale. So as long as you can break up that scale and the scale has a place to go. So let's suppose where you have an ID restriction, that the scale can actually fall through that ID restriction, and then you can continue to pass through. Yeah. If I have an absolute wall where nothing can go, all I'm going to do is just pile that rubble on top of that wall and basically making big pieces into little pieces into powder. Yeah.
Yeah, I think small bridges, You know, we've had experience where we've tagged a tool, pulsed, and continued on. If this is for hundreds, thousands of meters, you know, I think there's some applications, and we'd have to look at each well specifically there. I think the challenge that customers have is they never know how long that bridge is themselves. Can you remove LCM materials from plugging into screens? We've got some case studies. We just completed a well in Southeast Asia with this particular problem with a lot of barite that did some production logging on that. So the answer to that is we have experience with that. We do have some case studies on that one.
Yes, I guess it really depends on the LCM material. So if you can imagine something that's like those I want to say very, very fine plastic mesh or walnut shells or the like. So now you have an item that's physically bigger than the actual screen mesh themselves. So if that material was actually a brittle material, we could break it up. But if it's a very plasticky material, let's suppose you have those really lots of those plastic flakes, those are matting up against the screen themselves. That is a very difficult problem. And see, unless you get them smaller than the idea, you're not going to be able to get them to come through. Yeah.
Okay. God, sorry, we've got a bunch here. So I was listening to Chuck and not reading ahead, but here's a short one. So any ideas on how to treat res punch screens? So I think we dealt with that one just a little bit.
Yeah, so a punch screen, that's a key part about it, is it has a tortuous path. And I say what we've observed on some of them is that we may need a higher pulse density because not as much is actually getting around. But it really depends on how far we have to, how many levels we have to wiggle our way through a punch screen.
Okay. Here's one more. Again, it goes back to more pliable materials, but can we treat wax?
So we have tried to treat wax. So what we observe, you can imagine taking that sledgehammer and hitting jello or hitting rubber. And I say that in each case it just deforms and oozes, but it really doesn't break itself up as much with Shockwaves. That's really an application where you need a different type of technology to actually work with that pliable material. Yeah.
Okay, I think I got this one already. Has it been tried, Chuck? And I know the answer, we have done some open hole and we're doing some R&D work, but Damien asked, has it been tried in an open hole section?
So there was actually one of the case studies, which actually wasn't part of the paper, which we did separately, was a very remote well where they actually needed to do a drill stem test. And they actually used WASP to stimulate some of that damage zone or completion in. So that being said, it can be done, but it's an area that really needs further knowledge in going in. In that particular well, they actually were able to actually get more flow, but the methodology would stay the same, where you have a brittle type item, whether that be a limestone or actually that calcite, which is gluing the sand grains together in a sandstone. Being able to break that up over a short interval or depth of investigation can actually cause things to flow better.
Yeah, Muhammad's asked a couple questions here, so I'll grab this one. Have you used WASP for different purposes other than scale? And I think you just kind of addressed that with wax. Fine migration, I think we have multiple case studies. I think the challenge we have with a lot of our wells we treat is sometimes our customers themselves don't know exactly what's causing the production problems. But yes, we have surface testing where we've done more than just scales on top of multiple different types of scales. Any logging, let me just make this live. Any logging experience to avoid stimulating water zones amongst these case studies? I don't think it was any of yours,
Yes.
but we have done some in California, I know for sure.
Yeah, I mean, anytime you have that improved information, you can do a much better job of your task. Yeah,
yeah, we love data. So whether that's through tubing, formation data or caliper data, all data is good to us. Oh, here's one. Get your calculator out, Chuck. To treat 100 meters of sandstone on wireline, how much time and runs would you need? So I think let's come back, and I think I'll make this one live, and we'll touch on this real quick. But I think this is one that we should follow up with this customer on. Is I think we need some more information on what the actual challenge is in that particular, as Chuck talked about. Calcium carbonate breaks up a little easier than barium sulfate. If we have a good indication of what that challenge is, I think that would help. Again, completion size that we're in. So there's a few. I don't think it's an easy answer to say.
Yeah, I mean,
we could do it.
You can't have one cookie cutter to solve every problem in the world. What's key about our process is we actually look at the well parameters and then customize it from there. With what we know, some things will take a bit more, some things will take a bit less. Yeah.
So this is the last one I have. So if there's any more real quick, please send them in. But how about breaking sludgy polymer debris with entangled sand and scales? I like it. This
we
is a
actually
customer that has this problem.
So about 3 years ago, we actually did a joint partnership with a polymer company where we actually looked at using those shockwaves to actually break up polymers. So as you can imagine, where you have that non-Newtonian fluid and you were to snap it, we actually did observe that with those repeated snaps or high shockwave pulses, we actually could start breaking up some of those polymers. And actually we observed that actually over different numbers of pulses, we actually saw a decrease in viscosity. That the application they were looking at was actually kind of weird, but where people put in too much polymer and actually gummed up a well. So it did look like it did have application to do that, but no field trials were actually performed with it.
So again, if there's any additional information, any additional questions on any of these, that's it. That's all we have for questions right now. So I just want to take real quick. I want to thank Chuck again and Stephanie for organizing this. And I want to thank all the customers for joining us. We appreciate you taking the time. Oh, and I got one more. Any loss of PI observed? So we'll deal with this one real quick, and then I think we'll shut it off. So I don't know if this is particular to
productivity index. Yeah, so basically well got worse. Yeah. So with that being said, so one of the items which we talk about is that if we don't have enough energy, so we're really affecting that narrow radius around the well itself. We're going into wells where nothing is flowing. So typically we're not, so with that being said, if the item relates to a blockage of flow, we're breaking up the structure of those items themselves. So if we're going to be breaking up the structure, I can't see why the PI would be going less, because we'd have to have something that would actually cause it to compact or restrict itself. So we haven't seen that where we've made wells worse, and that makes sense why we haven't yet. So,
okay. Again, appreciate all the questions. Appreciate the interaction. We will be having another webinar actually next week where our operations director, Rob Harris, will actually be demoing the technology. So we're going to bring you guys into our facility. We've done this last week with a customer. Worked actually pretty good, where you'll see the tool pulsing, you'll actually see the tool. So we'll send out that as well on LinkedIn and some other social media, as well as we'll send off some emails here to customers to see if they're interested. If anyone wants a specific demo related to your specific problem, please reach out to either webinar@bluesparkenergy.com, myself, s.patton@bluesparkenergy, or you can always talk to Chuck as well at c.fensky@bluesparkenergy.com. Again, thanks everyone. Chuck, you got any last words?
No, I mean, so it's one of the things that we're really passionate about, and we're hoping that this can be a solution for some of your challenges as well.
Excellent. Stephanie, thanks again. Thanks again, everyone. Good evening, I guess, to most people. It's bright early here in the morning for us, but good evening to you guys. Hope everyone's safe and healthy, and we'll talk soon.
Thanks again.
Thanks.